Okay, hello everyone. Welcome to today's talk from Dr. Subhankar Pal. Uh, Dr. Subhankar Pal is a staff research scientist in the Efficient and Resilient Systems group at IBM T.J. Wilson Research Center. He's broadly interested in computer architecture and hardware-software co-design. He presently works on accelerating homomorphic encryption and early-stage design space exploration of systems on chips. So the mic is yours, Subhankar.
Yeah, thanks, Steve, for the introduction. So I'm going to be talking about a lot of basics and characterization work and an approach I co-developed to improve the efficiency of pruning methods for machine learning under homomorphic encryption. The characterization work is going to be more general. The second half of the talk will be a little more focused on privacy-preserving machine learning. So let's get into it. So the first piece of work I'm going to be talking about is based on the characterization study that I had done a year and a half ago. So all of this is going to be from a perspective of a computer architect, such as myself. So a lot of the math has been distilled down to something that I can understand, and I think the architecture community can also appreciate. I just want to start by saying there's a lot of math behind FHE, and if anybody is curious to learn more, I have a lot of pointers to different papers that can explain it with. What is privacy-preserving machine learning? Using homomorphic encryption or HE, we basically consider a client and a server. So there's a client side and a server side on the right. So let's say the client wants to run inference on some private data. For example, this could be a hospital being a client. They want to run inference on patient X-ray images, and they're offloading the inference job to a third-party server, which they don't trust. So how can one use FHE for this? So you have some private data. There's a first step called encode and encrypt, which encrypts the image. You send it over some trusted transmission line or untrusted transmission line over some protocol such as TLS. And on the server side, you would run a prediction, which in this case would be a neural network inference. And then the server produces an encrypted result. The server has no visibility to what the contents of the results are. It simply sees it as a bunch of garbled data because it's encrypted, ships it back to the client, and the client has the key to decrypt it. And there's a step called decode as well. And then maybe unfortunately, this patient had code. So that's the basic flow of privacy-preserving machine learning using FHE. It's one of the most common use cases that we're interested in, and most of industry is also interested in. But there are other areas that FHE has a lot of scope, such as financial transactions, database applications, and so on. So I'll be going into a little bit of math, but not too much, so as to not overwhelm people. But what exactly is involved in FHE? I will first talk about the encrypt, encode, decrypt, decode, these four steps, and then I will later talk about the inference part. So to start with, you have a bunch of data. These are complex numbers. And by the way, I would be talking about a specific FHE scheme called CKKS. And that just stands for the first initials of the authors. And so we have a small n number of elements, each of which is a complex number. There's a capital N, which is called the polynomial modulus degree, not important right now. But we have to go first from this raw data into the plaintext space where this is all represented using a polynomial. So this notation belongs to Z just means it's an integer. All of these coefficients of the polynomial are integers. And this is the plaintext. Further, to go from the plaintext to the ciphertext, we have to do another step called encrypt. And the ciphertext actually consists of two polynomials, A and B. So this is the notation one might see in many papers. The encrypted version of M, which is the original message, is AX and BX, which are two polynomials. BX expands to this, and I will go over the individual components. So A of X is a polynomial with random coefficients. S of X is the secret key, which is only known to the client in this case. M of X is the encoding of the message. I will explain how encoding works. And finally, E of X is a small polynomial with Gaussian coefficients, which is used to introduce small Gaussian noise into the system so that it maintains a security which is based on the foundation called learning with errors, or LWE. One can look it up. So now the point is the coefficients of the polynomials are ZQ. ZQ just means it's an integer modulus a big number Q. Q is a large integer, typically several hundreds of bits long, and there's a special format called residual number system that is used to represent such a large value in modern machines efficiently, and I'll come to it. So after you do encode and encrypt, you kind of have this A and B. You can imagine A and B as two tables. So now we have kind of expanded it or horizontally into something called limbs. So what limbs are the decomposition of the value for each of the primes in the RNS space, or the residual number system space. So how RNS works in Jiffy is basically you decompose Q into product of coprimes. And for each coprime, you have a corresponding component of the original value. So for example, A00, A01, A0L, and so on represent the RNS decomposition of the original coefficient. So now you can view this as a kind of a 3D tensor. So you have n coefficients along the rows. You have L+1 limbs along the columns. And then you have the A polynomial and the B polynomial separately. And that's your single ciphertext. Now, if we want to quickly do some math and check out what's the data expansion factor, so how much does the data expand when going from the original message to the encrypted space? It's of the order of, let's say, 50 to 100x usually. If we plug in some specific numbers, in this case, it comes out to be 64x. So that's a real problem because you're going from, let's say, a single megabyte to 100 megabyte. That's a huge expansion factor. And that really bottlenecks the or puts pressure on the memory system in modern architectures. Okay, so now we'll go through some concepts in CKK-based FHE. One important concept is limb dropping, which is used for doing multiplications. So how do we do multiplication of multiple ciphertexts? So you could take an approach such as this. Now, I didn't go into it in too much depth, but because you started with complex numbers, you can represent floating point values, but they're not technically floating point, they're represented in fixed point. And you might know that fixed point numbers are associated with a scaling factor, which I should call as delta here. And when you multiply two fixed point numbers, each with scaling factor delta, I will come to this, the result is A times B with a scaling factor of delta squared. Now we have to go back somehow to the original scaling factor. And for this, we do something called limb dropping. Now I need to talk about this modulus chain. Each ciphertext is associated with a set of QI values. These basically tell you how many limbs are remaining in the ciphertext. So if there are 3, then you can just do 2 multiplications before you run out of limbs, because you cannot do a multiplication on the last limb, because if you remove the last limb, then you have nothing left. So going back here to go from delta squared to delta, you need to drop a limb. So it goes away from the modulus chain. And if you just multiply it twice, you kind of see that you have only one remaining, one limb remaining. But one could do some compiler transformations to reorder these operations, and approach 2 shows that. So if you multiply AB and CD in parallel instead before multiplying them together, you'll notice that you have one extra modulus in the chain remaining. What that means is on the left case, you have no more operations possible. On the right case, you can perform one more operation. So in this simple example, it looks like a very insignificant saving, but in reality, such compiler transformations play an important role. So fewer the limbs dropped, shallower the circuit. So by the way, these data flow graphs are called FHE circuits in literature. Shallow the circuit, greater multiplicative depth remaining means you can do more multiplications before you run out of limbs. And what happens if you run out of limbs? I'll come to it later. Okay. Next is another factor that makes FHE interesting and challenging is the levels of parallelism and data interaction. So this is a single polynomial. Again, I kind of transposed it. Now you have the rows showing the limbs and the columns showing the coefficients. So there are certain operations, or I call them primitives in my slides, that operate along different dimensions of the data. For example, there is a kernel called number theoretic transform, or NTT, that operates across the coefficients of a single limb. So there is no data interaction across the limbs, but there is data interaction across the coefficients of a limb. There are other primitives. One is called base conversion, or bcon, that operates in the other direction. So in particular, there's a reduction kind of operation along the limbs of a given coefficient, but no interaction in the other dimension. There are other operations which are simpler, like simple modular addition, which are element-wise. And then there's a final level, which is outside of all of this, where you have multiple parallel operations. Then one can think of how to map the different operations onto different hierarchies of the hardware as well. So this we are calling as ciphertext-wise parallel operations. Okay. So now I'll explain some of the data flow graphs, very high-level ideas about how the operations actually work. Unfortunately, the notations are not very consistent in literature, so you might see some variations of the terms I'm using, but bear with me. So now we have a single ciphertext again. I'm showing a condensed representation. So what can you do with this? Well, you can take a ciphertext, you can add a plain text to it, which is shown with this M prime. That's the other message. So you can do PT add of a ciphertext with a plain text. Similarly, you can do ciphertext addition. You can do subtractions. You can do multiplication of a single scalar value with the ciphertext. You can also do multiplication of a vector value with the ciphertext. In this case, there is this rescale primitive that you see. This basically implements the limb dropping that I discussed a few slides ago, but I'm not going to go into too much detail on that today. There are more complicated ones as well. This is rotation, and this is multiplication of two ciphertexts. Of course, the rotation is on a single ciphertext. And there is a like a subprimitive called automorphism. It's basically a structured shuffle of the elements of the polynomial, but there's no actual computation involved. And then there's a step called relinearize. It's also called key switching. Maybe I can explain it a little bit. Basically, for example, if we look here, we're multiplying two ciphertexts. So there's an A component and a B component. When you multiply them together, basically the secret key that encrypts the ciphertext changes to S squared from S. And it's similar to how the delta factor changed from delta to delta squared. If we don't do something at this step, you cannot keep cascading multiplications back to back. So what we do is relinearize the key that encrypts this intermediate ciphertext back to S. And it's a very nuanced process. There are a lot of operations involved. In fact, the execution time, we profile it to be over 90% of the entire primitive itself. So this is an important step. There's a reference 3, I have it in my later slide, that provides an explanation of what exactly goes on inside relinearize. Okay. A lot of us have heard about NTT and INTT being very important for FHE. Why it's important, it's pretty apparent. If you want to do polynomial multiplication using like a textbook method, it's an order of n squared operation because it's essentially a 1D convolution. So using NTT is similar to applying FFT for electrical engineering. It reduces the overhead from order of n squared to order of n log n, but you have to obviously do an NTT and then an INTT at some point. but it is definitely worth it because the number of elements we're looking at is usually 2 power 14 to 2 power 17. So it's a lot of values. It's not feasible to do convolution on that. The data flow is exactly the same as a textbook FFT algorithm, except the addition, subtraction, multiplication are all modular addition, subtraction, multiplication. So in some literature, we see the notion of coefficient representation and evaluation representation. Basically, entity takes you from coefficient domain to evaluation domain, and identity is vice versa. This is also called double CRT, stands for double Chinese remainder theorem. That's something we could come across in literature as well. Okay. So I talked about limb dropping, but I did not talk about what happens when there is only one limb remaining. So that is resolved with something called bootstrapping. It's a very expensive procedure, but it basically cleans up the ciphertext. It restores the limbs of the ciphertext, and you can again repeat the multiplications. So you can kind of chain together multiple sets of multiplications. And there's a nice visualization from another paper. So this one talks about the multiplicative budget on the y-axis, means how many multiplications can you do before you run out of limbs. So kind of goes down as you do more multiplications, then you do this bootstrap. This bootstrap doesn't bring us back to the same multiplicative budget that we had before, but it brings us close to it. So this is some notation from the paper, but basically you have L minus L boot number of levels remaining after each bootstrap operation, but this allows you to do theoretically infinite number of operations. And that was the breakthrough that put the fully part in the FHE in the first place. There are different variants that we study. The details are here. I'll talk about it later. So maybe I'll pause here before I go into some experiments and characterization that we did. Any questions here? Guess not. Okay, then we can go on. So we used HElayers, which is a tool developed by my colleagues here at IBM. It's being actively worked on. There is a version of it that is public, which is the API layer and the workloads. The code itself that implements HElayers is not public, but one can go into these websites and check out how to use it. And there's a Docker image that helps one set it up as well. Basically, it's an SDK. So the idea there is to go from high-level PyTorch or TensorFlow code down to FHE-friendly versions of the code to run inference or training, or even like simple things like regression. And it has these multiple layers of the stack that eventually lead to talking to the hardware, which could be a CPU, GPU, or OPU is other processing unit. And it interfaces with these third-party libraries. Those are the ones we have characterized. In particular, we looked at Seal, OpenFHE, Heian, and Latigo. Out of these, Heian is the one that's closed source, but that's also the best performing. So this is a year old, so I'm sure that OpenFHE and others have made strides. So some of the performance numbers might need to be updated for a bit. And we have done some evaluations on CPU and GPU both. And I'll show some data. This one is not important. Let's just talk about the characterization here. So the first set of numbers I show is performance scaling with number of threads. So we picked a certain parameter set, which is, I would say, typical for the applications we were looking at. So we can see basically performance scaling for all of the primitives. The primitives are shown on the x-axis, saturate around 16 cores. The y-axis shows the time. And the reason I have divided the graph into three sets is there is an order of magnitude difference between these primitives. So for example, relinearize takes at least an order of magnitude more time than multiplication or addition or others. And then bootstrap takes a couple other orders of magnitude more time than even these relinearize, rescale, rotate operations. But then relinearize and bootstrap are composed of these lower level primitives, one can say, along with other operations. So you can think of these as kind of macro primitives. But these are indeed very expensive. So you can see this takes up to seconds on a real process. If we compare different libraries that I showed, and only for Hyan we were able to compare a GPU version. I believe now OpenFHE I think has a GPU version, but we did not at that time. So these are the results, and we can see, let's compare CPU to GPU first. There is at least 1.5 order of magnitude speed up with the GPU for the Hyan library. Should be similar with an efficient GPU implementation for any of these. And then by itself, Hyan was doing much better, 1 order of magnitude better compared to the other CPU versions of the libraries. In terms of power, these are some of the power numbers. One can look at these slides later on, but the conclusion here is, so out of all of the libraries, Hyan was the one that performed the best, but it also consumed the most power. So it consumes 2x more power compared to other implementations, but is 10x faster. So about 5x improvement in energy efficiency on a real system compared to the other libraries. Okay. Next, we looked at an inference workload. This is kind of a simple neural network composed of just 3 layers. The purpose is to do detection of credit card fraud from transaction data, but encrypted with FHE. And the data set we got is from Kaggle, and it's listed here. So this is a use case in financial transactions and encrypted machine learning as well. The network looks like this. There's a fully connected layer followed by a square activation function. Now there's a problem with FHE, which is you can't represent nonlinear layers directly without some sort of approximation, because otherwise you cannot do polynomial math on them. So the simplest representation is a square. And then, as I mentioned, there are 3 layers, and then the idea is to just detect whether a transaction is fraudulent or not. And this is kind of the workflow, but I will just explain the high level of it. You're loading the model and the data set on the client side, doing some setup, encoding and encrypting the model itself, and then encoding and encrypting the data, sending it to the server. The server performs the encrypted inference and then sends it back to the client, and then the client decrypts and decodes the predictions. One thing to note is the model only needs to be encrypted and encoded just once. You can keep reusing the same weights for multiple inference runs, just similar to traditional machine learning. Okay. This is how the network looks like in the FHEized form. Looks complicated, but it has the same primitives that I talked about before. So there's a bunch of multiplications and adds, narrowing it down to a single ciphertext. And then there's rotation and summation to do the reduction, the dot product and reduction. And basically this left side is the first layer, the middle one is the second, and the right side one is the third. And in terms of performance evaluation, maybe I'll just go to the next slide. Yeah. So here we can look at the kind of segmentation of different parts of the operation, because obviously Amdahl's law would kick in if you just look at inference. So we have looked at initialization of context, initialization of model, encrypting, and it also consists of encoding, the inputs, the activations, and then the actual prediction runtime, and finally the decryption of the result. So for different batch sizes, we see with the different colors, the execution time. This is on a GPU, by the way. So let's look at some analysis. The encode encrypt time, which is shown here, linearly increases with batch size, because with the increasing batch size, if you just take a look at the number of ciphertexts, it kind of grows for inputs, weights, and biases, all of them. So kind of makes sense that the runtime would increase. Another thing to note is if you look at just batch size 1, then the encrypt input time is about 40% of the prediction time. So which means because you have to do encrypt input every time you do a prediction, it would be a bottleneck eventually, because if you accelerate just the prediction, it's not sufficient. Amdahl's log n. And finally, this prediction takes a U-shaped graph, which was interesting. So we looked at it a bit more, and there are two opposing factors. With increasing batch size, there are more ciphertexts, so more computation time that we get from here. But and this one shows a pie chart of the primitive-wise breakdown of the inference time. Shows that actually with more batch size, the way HElayers does the packing of the operations, the number of rotations actually goes down. They're converted into additions, and additions are like an order of magnitude cheaper than rotations. So more ciphertext, but fewer rotations. So eventually the execution time kind of wins down and results in this kind of a U-shaped graph, which was interesting. So yeah, this concludes this first half of the work. So we did characterization of basic FHE primitives and a real-world FHE workload, and took away several takeaways from this work. And one thing interesting was it is important to accelerate encrypt encode in addition to just the inference part. The decrypt decode part, because it's just an array of the prediction values, it's less important. But also the operations are kind of simple compared to encrypt. And yeah, we have some investigations on deeper insights into some specific primitives and bootstrapping, but due to lack of time, I won't be presenting that today. So I'll pause here before I move on to the next piece of the work.
Okay, cool. So any questions from the audience? So if you don't want to talk, you can type it in the chat. Okay. So yeah, then I have a question to start with. So my question is, I saw the 3-layer MLP that is, and the activation function seems to be the square, right?
Yeah.
Is that square used throughout all 3 layers, or just at the last layer?
No, it's used through all 3 layers. The last layer is actually softmax, and softmax you can do in either the client side, in which case you will do a regular softmax because you would do FHE decrypt decode and then you would do the softmax. But if you want to do it on the server side, it has to be approximated because softmax is exponential function. Again, it's nonlinear in that sense. So yeah, anything nonlinear has to be approximated.
Yeah, but the choice of okay, yeah. So in that case, the choice of the square in this case makes sense, right? Because it's easier
It's
to.
a simple network, exactly. It's a simple network. But if you imagine the graph of the square function, uh, if you go too much to the left or too much to the right of the origin, then it deviates very much from ReLU or GeLU or other activation functions. So in that middle part is where the square is kind of occasionally approximating the ReLU function, for example.
Hmm. Okay, cool. Yeah, we have one question from the chat. What mathematical operations are commonly used in bootstrapping or encryption?
So interesting question. I'll talk about encryption first. I kind of went over it, but let me see if I can go back to the slide. It's basically all modular multiplications, additions, subtractions. Let me just go back to animations. Yeah. So this is basically encryption. So the exact equation is S of x times A of x. This is element-wise multiplication, modular multiplication, and then element-wise modular addition. And then there's a negation at the end. Bootstrapping is much more complicated. There are 4 high-level steps. I'll just name them. I'm not going into it. The first one is mod raise. When you start with only a single limb, remember when we only do bootstrapping when we have usually one limb left. We want to go back to the original number of limbs. So you do mod raise, which expands the number of limbs, but then there are a lot of mathematical operations actually required to basically make sure that the error is removed, because if you just expand the ciphertext, it has an error component. The error component also grows, so you have to kind of refresh it. And so there, the basic operations are rotations, ciphertext multiplications, reduction, yeah, and so on. But lots and lots of them. So because you can also see it in the execution time, it takes several seconds.
Hey, cool. Okay, we do have more questions? Why do we need two polynomials to represent one plain text vector?
I didn't show the decryption equation, but basically you need to provide to the user the A of X part to be able to undo this encryption. If you don't provide the A of X part, if you just have this polynomial, there is no way to get back M of X. And I have some pointers to some of the papers that show the decryption equation. It's very simple. If you give it a read through, you can understand it.
Okay, thanks. Yeah, probably we need to move on due to
Okay.
topic. Okay.
I 133. Okay, I'll try to do the second part first. Um, while I scroll through. So after that, we looked at, okay, what are the machine learning techniques we know and what can we use for machine learning under FHE? So we thought of pruning as the first step. And these are some of my colleagues who helped with the work. We all know pruning. I'm going to skip this part. What we need to remind ourselves is we are dealing with not a single number, but a bunch of numbers. Particularly, if anyone remembers, it's capital N over 2 numbers put into a single plain text or a single ciphertext. And that is around 2 power 13 to 2 power 16 values considered into a single packet. So FHE literature terms it as SIMD, which is different from our SIMD in the sense of computer architecture, but kind of similar because you have a bunch of data and you're performing the same operations on it. So for example, if you want to do addition, it's element-wise addition, but it's not like you can individually cherry pick and add A0 to B2 or A2 to B1 and so on. You have to do it in this packetized form. So therefore, you can kind of start to think about the challenge, right? If you just do simple pruning, there's no benefit because if you, for example, here, if you have pruned out A2 and A4, you still have 3 values left that are non-zeros. So once you go into the encrypted domain, zeros are not represented as zeros. They are garbled. They're randomized, not randomized, but they look like random numbers. So there is absolutely no benefit to any hardware support you may have for pruning, like zero skipping hardware or anything just becomes useless. So to be more precise about now going into some HElayers specific details, how do we do this actual packing, going from the raw values to a packed plain text or a ciphertext? So this paper here is by my colleagues. They propose to pack the raw data into something called tile tensors. And this is how HElayers also actually works. So let's say you have this raw 3 by 6 matrix of data. You want to pack it. What HElayers would do is, depending on the operation, of course, but let's say here we wanted to run it through a dense layer. This is the first layer of the network. Then we would, and let's say we picked a tile shape of 2 by 4 by 2. Again, different layers have different tile shapes, but let's just talk about 3D tiles here. The way you would packetize this is you can divide this raw data into subtiles, or I guess these are just called tiles, but you would have these boundary cases where you have to do zero padding on both sides in this case. And along the z-axis, you have to do replications to be able to match to the other tensor that you're doing the operation with. In our case, if imagine this is the activation, then for the weights, you have to also do some replication. Again, this paper reference 5 explains exact math of how this works. But the high level idea is you would go from the raw plain text, raw message data into this kind of a tiled data. So what we have to worry about is tile sparsity, not individual sparsity. That's the main point I'm trying to make. So for example, if you take this tile, 0400, blah, 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 even if all of the other values were zero, there's a 4 here. So you cannot just throw the 4 away. So you would have to have all of the values being zero to pack them into a entirely zero plain text or ciphertext. So how do we do that? So the method I propose is rather simple, and I'll visually show it for ease of understanding. Let's consider a single dense layer represented as a 2D matrix here. Let's say we just do simple threshold-based weight pruning. And this is the resultant matrix. This is the resultant visualization. And if we pack this into 2x2 tiles, remember that the Z dimension is just replication, so I will not show it for clarity. So if we pack it like this, we just see that there's one tile, single tile that has all zeros. So the savings is 1 out of 8. Instead, consider that we permute the rows and permute the columns. So what that means is, visually speaking, you have just reordered the neurons. That doesn't affect the functionality of the network. And once you do that, you have this transposed or permuted, I guess, weight matrix. And if you pack that, turns out for this example matrix, the best you can do is you can remove 4 2x2 tiles of entire zeros. So you can kind of get an idea of the method. But if you do an exhaustive search to find the best permutation, then it is very prohibitive because the complexity is order of m factorial times n factorial. So we have to use heuristics. And here is one heuristic which we propose in the paper. So here's another example of a matrix. The idea is first to split it into rows and consider each row as, in this case, an 8-dimensional vector. And by the way, if you packed it at this point, you would have just 1 0 tile. Instead, we will run it through a k-means algorithm. So here we have 4 vectors, and we want to create 2 classes, right? So we feed that information into the k-means algorithm and run it, and it produces a reordering of the rows. And now if you packed it at this point, you have 2 0 tiles, but maybe you could do better. So what you do is transpose it and then treat the columns as the rows and run it through the k-means algorithm again. And it gives you another reorder. So if you keep doing it, you would get the maximum number of 0 tiles. There is no formal proof of convergence in our paper, but empirically, I have for all the workloads I've evaluated, there has been convergence using this method. Now, there are some nuances. Those details are in the paper, but we had to use a custom Hamming distance called grouped Hamming distance for the distance function. And every cluster has to be balanced, if you think about it, because the tiles are equally sized. So every cluster or every class has to have the same number of vectors in them. So I had to implement a balancing scheme for that to work. But this is the overall idea of the permute algorithm. The biggest challenge was how do you do it for multiple fully connected layers? And then we will talk about convolutions later. So for a single layered NN, the visual representation is this. You just permute the rows, permute the columns, and keep repeating until convergence. But for a multi-layered NN, how would you do it? Well, you can do it this way. You can kind of structure the weight matrices like this, imagine them like that. And then what you do is a co-permutation. Basically, think of it as we are reordering the neurons of a single layer, but it's affecting the weights to the left and to the right, right? So you're kind of permuting, for example, WAB and WBC transpose together, and you're permuting the columns in the other direction. So for example, WBC transpose and WCD, and you permute the columns. And you keep repeating that till convergence. Now, why do we do this? Because if we go back to the previous method, the activations, you can imagine, also would have to be permuted, right? To the left and to the right. And if we just analyze this separately for each layers, then what you need is, after a layer, you need a permute layer for the activations. And then you have the next layer, and then you have a permute layer. If you have a permute layer after every actual layer, then it becomes a wash. There is no benefit with this approach. Instead, with this method, you would have to have just one permute layer in the beginning and one at the end, and there is nothing to be done in between. So this was a nice approach in my opinion. For convolution layers, I'll just go over it really fast. But the idea is it's a 4D tensor, so it's more complicated than a 2D weight tensor. So what we do is we first reshape, and we do something we call column group-wise transposition. So you have groups of columns, you transpose them, and then you would feed each group into the k-means algorithm separately. And then you reshape it back to the 4D tensor that it was. That's the high level idea, but the point is there's no need to do it online. This is only done once offline prior to the model deployment stage, so it doesn't affect the runtime for the inference at all. And we looked at different pruning schemes. We tried to do different steps like train, prune, permute. I'll come to expand, retrain, pack, or train, prune, permute, again prune as a second step, expand, retrain, pack, and so on. I will explain one of these methods. The method is called P4E. Basically, take a look at this MLP. The first step we apply is to do a pruning. We can do a threshold-based weight pruning, for example. Second step we do is to do a permutation based on the k-means algorithm I showed. Notice that initially we had 2 out of 22 zero tiles. Next we have 7, so it's increased. Then we do a second prune step to slightly increase the number of zero tiles. Basically, we look at tiles that have, let's say, 95% non-zeros, or sorry, 95% zeros. Then we make a call, okay, let's get rid of these 5% non-zeros in this tile. It does lower the accuracy, but then we do a retraining step to get back the accuracy. And then finally, there's an expansion step. So if you have tiles that have 99% non-zeros, then the idea is let's just make those 1% of zeros also non-zeros because they don't matter anymore. Instead, we can get back some accuracy with this expansion step. So this careful pruning method gives us a lot of benefit for actual tile level pruning without a lot of drop in accuracy. In this case, we apply 61% of, we remove 61% of the single weight values, and we get up to 45% tile sparsity. So this is the threat model for the evaluation. It's a two-party system, and there's a user, basically the client, who holds the secret key, and then there's a cloud who holds the evaluation in public keys. Basically, the client has the knowledge of the weights and the data, but the cloud learns nothing other than the structure of the neural network. So it learns, for example, if you started with AlexNet, it learns that you have pruned away certain parts of the AlexNet, but it doesn't know what those values are. So there is no information leakage with this method. So there were 4 applications we evaluated. There's an MLP classifier, there's a CNN classifier, there's an autoencoder-based compression network, and then there's an autoencoder-based denoising network. And then finally, I have not visualized it, but there is, we finally demonstrated this on 21-layer HE-friendly AlexNet with trained activation functions. What that means is, remember I was talking about X squared as the activation function for that simple credit card fraud detection network. Well, in this one, my colleagues had used a different approach to give us trained values of an activation polynomial, which is a several tens of degrees large polynomial to do a single ReLU approximation. So in terms of the number of operations, it's quite complicated. So these are the data sets we used. We used PyTorch for accuracy measurement. For the HElayers execution, basically, we took those zero tiles that we get from this approach. We tagged them with a Boolean flag that says it's a 0 or a non-zero, the whole tile tensor. And for the zero tiles, we just tell HElayers, hey, don't do any computation when you see a zero tile. And then you do a zero skipping in software basically, but at the tile level. And these are some of the parameters for the evaluation. So there was a competing scheme called P2T. Basically, P2T at a high level looks for entire tiles that can be pruned. So you can think of go tile by tile on the weight tensor, scanning through all the weights, and then look at the tile with, let's say, the least average of all the weights, and then remove bottom 10% or whatever of those tiles. So that would be the P2T approach versus our idea called HE-PEx, is that careful prune, permute, and then second round of prune, and then retrain approach. And for different tile shapes, we did this evaluation. So these are the height and width of the tiles. Remember that the Z dimension is just the replications. But so if this is T1 and T2, then T3 has to be, or T1 times T2 times T3 has to be n by 2. That's the number of slots. So just respecting that equation, we have done these evaluations. And we can see as you increase tile sparsity, the accuracy would go down. There's a point at which the network breaks. And you can see those as the sharp falls. So with our methods, and these are different variants, I didn't get time to go into details. But if we say we want to stick within 2.5% of the accuracy of the original network, then that model is shown with the red marker here. So the conclusion is you can get a tile sparsity of up to 84% with a worst case accuracy drop of 2.5% over the unpruned neural network. And in terms of improvement over P2T, these are some of the improvement numbers. So we can get up to 2x more number of zero tiles for a larger tile shape against this competing approach. Why does P2T have such a sharp drop? You can think of it as the larger the tile shape, the more the chance that while pruning out an entire tile, you have a high variance in the weight values. So you're pruning out a lot of insignificant weights, but you also might be pruning a couple of very high valued weights. So the higher the variance of weights within a tile, the more risky, quote unquote, it is to prune that tile away. And the moment you do that, you have this huge sharp drop in accuracy for that particular pruning configuration. But at the end, we don't really care about how many tiles we have removed. We care about the latency and memory and the loss or the accuracy. So these are some of the numbers for different tile shapes. This is the normalized latency compared to the unpruned network, and then the normalized memory requirement, because obviously you have storage savings as well, in addition to execution time savings. Yeah, so all in all, we saw 10 to 35% reduction in memory and up to 35% reduction in latency, while remaining within 2.5% degradation compared to the unpruned model. So one question could arise, how do we choose T1, T2, T3? Well, that depends on factors such as the batch size. If you have more batches, turns out you can have less replications. So you can go smaller on T1, T2, you can have more T3. But if you have a batch size of 1, then you would probably want to go higher on T1 and T2. And that original tile tensors paper that describes HElayers, which I've linked to, that describes what is the effective way to choose T1, T2, T3. So that's kind of a separate work from this. In terms of number of operations, so we looked at different tile shapes, looked at number of additions before and after, multiplications before and after. So we see a lot of significant savings. But there's one data point I'd like to focus on. So this data point, the 8x8, even with 99% tile sparsity, that data is not shown here, but that data point is showing that a network which has been pruned to have 99% tile sparsity, that still has potential 37% latency to reduce. So there's a lot of leftover latency and memory from the parameters. And why that arises is okay, you have sparsified your weights, but if you multiply it with a dense activation, then you would have a denser activation for the next layer. And you're not doing anything to the activation functions. This is not exploiting activation sparsity in that sense. So we can use other methods like activation pruning to get rid of that remaining latency. And remember that the polynomial activations are very deep, so that does consume a lot of latency. And we're not doing anything to prune there. So I think that's it. Yeah. So kind of went over this work really fast, but we exploited a bunch of basic ideas, pruning, permutation, tile expansion, and packing to show benefits for neural networks under FHE. We evaluated it with HElayers, and the P2T scheme that we compared against is based on a prior work called Hunter, so we showed some benefits there and compared the neural network loss accuracy with the percentage of ciphertexts eliminated. And yeah, we showed it for a bunch of different applications. We have work in progress to use this approach for transformers and other language models. But for this, we just wanted to stick to the basics. We showed it for MLPs and autoencoders. And yeah, that's it. I'll pause again before I just have a final slide on our current and future work. Any questions?
Okay, cool. So any questions from the audience? Yeah, so on my side, I do have a question. So I saw you already show that, for example, the choice of the tile size do have a significant impact on the overall runtime because that's definitely a trade-off between the accuracy and also the valid computation you have to do, right? So do you think this is one form of structured sparsity? Because at the very beginning, you showed that if it's very fine-grained, you might not be able to leverage one a full ciphertext for all possible slots, right?
Yeah. Yeah, so this is indeed a form of structured sparsity. I guess another way to look at this work is I was trying to convert unstructured sparsity to structured sparsity after the fact. So I think we could do analysis of competing work in the regular machine learning field, not encrypted, that deals with generating structured sparsity in data. It is just that the shape of the tiles will be dictated by an external factor, in our case, HElayers, because that depends on whether you're prioritizing low memory, low latency, high throughput, or what is your optimization criteria.
Okay. Yeah, so I think, for example, NVIDIA, their GPU has 4 to 2 or 2 to 1 sparsity, right? So those kind of, is it possible like to convert this kind of, hardware concept into the FHE? I mean, but at more maybe at the software level so that you can sort of have a released constraints on such sparsity?
Yeah, I would see that as a starting point. So instead of doing individual threshold-based weight pruning, we could start with a 2:1 structured sparsity, but then it's still not packed into these larger tile shapes, right? Like if you think about 8 by 8, it's 64 consecutive zeros that you need uh, within a tile. For 64 by 64, it's much more. So unless there are prior works that I'm unaware of, I don't think structured sparsity deals with such large holes in the tensor.
Right. Okay. So any other questions from the audience? Okay, if no, probably that's the Subhankar, you
Yes.
have one more slide, right?
Yeah, I have one just like a kind of a teaser slide on what we are working on because the work I presented is based off of like a year and a half old work. So since then, we have been working on architectural ideas to accelerate FHE. So in the reference 9, which is a Cal paper, we proposed this near DRAM-based entity accelerator called Dramaton. The high-level idea is to have the computing units near the DRAM banks and use a different kind of entity than the typical ones, which are Kuli-Tuki or Gentleman Sandy. This one is called a singleton-based entity. And then we show how to scale to multiple different large entities and kind of fold them down to a manageable number of P's. So this is just a teaser, and for more information, one can look at that paper. So since then, we have also extended this work to an HPM-based accelerator. That's actually, we're going to present it in HPCA. This one really deals with end-to-end FHE. In fact, we have looked at HElayers workloads, which was really good for us because HElayers is an end-to-end stack. So it takes your PyTorch networks and generates your FHE networks in graph form. And we have taken such compiler-generated workloads and run them through the simulator we have. Prior to this, as far as we know, others have just taken handcrafted workloads because there's also a lack of, or I guess it's changing, but there had been a lack of frameworks that produce FHEized versions of regular workloads without any human intervention. And so over there, I'm kind of biased, but I think HElayers is a really good tool to use. So yeah, this work would be presented at HPCA. And yeah, these are the references to all of the papers in the slides. And yeah.
Okay,
Thank you.
great.
Yeah.
So yeah,
Uh,
I'll be at SPCA, so hopefully I can get a
okay.
chance to talk with you in person. Yeah, so I think that should be the end of this talk. Let's thank Subhankar again virtually. Thank you so much, and hope to see you talk with you later. And definitely, probably will send out email to you if anyone is interested in your research.
Okay.
Okay.
Yeah. Yeah.
Okay. Sounds
Please.
good.
Yep.
Sounds good. Thank you, and
Yep.
see you later. Thanks
Bye-bye.
for attending.